makes this is a poor electrode. Okay. So generally we need some current collector to use in either in batteries or capacitors. Generally some metallic plates are used. So here this part is your active materials. If this active material doesn't have a proper conductivity, generally we'll go for some kind of carbon coating. Okay, the black color you can see in the outer wall. This is a maybe few nanometer thick carbon coating we will make, so that the lithium ion will diffuse through the carbon and will enter into the bulk material. And then this carbon also attached to this current collector, so that there is a resistance will be minimized. So instead of that, if this metal oxide or sulfate directly attached to this current collector, the resistance will be more. So this is what generally people will do that. But in the case of graphene, if you use a graphene sheet is a highly conductive. So graphene sheet itself can act as a current collector. Okay. If you put metal oxides over there or metal sulfide, in this case a tin sulfide directly to the surface, so this also cover this lithium, this carbon will cover this lithium ion, sorry, this tin sulfide. Because of this carbon coating is also not required for this material. So the diffusion of lithium ion length is reduced. So highly flexible, since the C6, this graphene sheets are flexible in nature, this could be used as a flexible electrodes too. So the other case, we will use some amount of binder. Okay, the job of binder is you have the current, this active acetylene black. This is a conductive carbon. So over there you have some metal oxides or metal sulfides. So it has to be binded with that. So we use generally some kind of organic or polymeric binder material like PTFE or PVDF. So this will also, if you use too much, then this will also create some resistance. So this is what generally it occurs. But whereas if you anchor this directly to this graphene surface, then you need not to worry about the binder molecule. Since this metal oxides or sulfide can be directly anchored onto this surface. So this is what you can observe, that you can intuitively, when you make some crystal growth over the graphene sheet, there is no binder is required. So this is chemically binded through some functional groups. Okay. So with this idea, we have made a graphene oxide solution prepared by modified Hummer's method. We add some tin chloride and thiourea. You want to have it reducing atmosphere, otherwise it will, the tin sulfide will become a tin oxide. It will not be a tin sulfide. So you need some kind of reducing atmosphere, like the ascorbic acid can do that job. So we can, once you make this, we have started with the graphene oxide solution. The graphene oxide has to be reduced to graphene. That can be done by either using a hydrazine solution, or you can also reduce this graphene oxide to graphene by hydrogen argon mixture at 400 degree. So we have done in both cases, and then we wanted to evaluate the performance. If you see the crystallinity, in the case of high temperature reduced in argon atmosphere, hydrogen and argon atmosphere shows some orthorhombic structure, whereas so hydrogen reduced material shows still tin sulfide. Okay, this is a bad tin sulfide, and then this is a commercial tin sulfide. You could see this is a SCM analysis, shows that there is a white patches over the graphene sheets. So this clearly shows that the uniform dispersion of tin sulfide throughout the nano sheets. Okay. So here this is a as prepared sheet. So if you enlarge the magnification, this is a 200 nanometer scale. But if you enlarge it, if you could see, this is a C60. This tin sulfide is uniformly decorated over the graphene sheets. So this is a reduced graphene sheet. You could see reduction through a hydrazine method, and then this case the hydrogen and argon mixture. This gas phase reduction. This is a solution phase reduction. You could see in the case of gas phase reduction, only few materials. The other side it is uniformly dispersed. So when you enlarge that solution-based materials to the high magnification, you could see there is a small crystals are decorated. So when you go for really high magnification of 1 nanometer, you could see this crystalline nature of this tin sulfide. in the graphene sheet. Okay, we also done some EDAX analysis to confirm whether it's, how much amount of tin is loaded on the graphene sheets. Then when you do the charge discharge analysis, you could see this is a as prepared tin sulfide graphene. You could see the first cycle is good. This is a generally is irreversible. When you go for second cycle and fifth cycle, and slowly this is going down. Whereas this is a hydrogen reduced, you could see this is so 900 plus. Okay, so even after 10 cycles, you could see it's almost close to 800 or 850. Whereas this is reduced in hydrogen and argon atmosphere. This shows relatively poor performance. This comes maybe here it's almost 700 or 750 milliampere hour per gram. You could see this is a solution reduced graphene tin sulfate composite, shows higher performance and compared to the gas phase reduced tin sulfate graphene sheets and then as prepared nano sheets. Even if you see the Coulombic efficiency, this is Coulombic efficiency for this particular one is solution based reduced is very high, and then even after 50 cycles you could see some almost close to 600 milliampere hour per gram of capacity has been retained. So we also done some rate capability for this. Then we in all these cases up to 0.5 or up to 0.1 is very stable. When you increase for high current, then this is capacity comes down. So why this capacity comes down at high current? So that is a problem with the lithium-ion battery originally. Since the power density of the lithium-ion battery is high, that means you cannot withdraw more amount of energy at a time. Okay, so that is a power density. That's why your supercapacitor comes into the picture, where the supercapacitor power density is very high, but unfortunately the energy density is less. I hope you are familiar with these slides. Because of this, only the charges are separated in conventional electrochemical capacitors. The power density of the capacitors are really very high. Okay, but the only thing is the energy density. Here we are talking about 600 milliampere hour per gram or something like that. Whereas if you come to the capacitors, the energy density in this case may be a 10 milliampere hour per gram, or if you convert into generally capacitors is reported by farad per gram. You also can able to report in milliampere hour per gram also. If you want to just compare it, this milliampere hour per gram of this capacitors maybe 50 or 60 milliampere hour per gram, maybe 110 or 1/50th of your lithium-ion battery capacitance. So this is the principle of supercapacitors. When you are charging, you are separating the charges to the opposite sides. So because of this you can repeat this number of charge discharge cycles say n number of times. So the cycle life of supercapacitors is very high. So that's what here this slide shows. So if you see the charge discharge time in the capacitor, conventional capacitors only picoseconds to milliseconds. In the supercapacitors are milliseconds to minutes, whereas batteries are in hours. Are coming to the life, if it's a 10⁴ cycle, okay, that's maybe almost a 10 to 20 years of life, I can say. But here maybe 5 to 10 years. But when you come to the batteries, really a year or two. Okay. So if you see the power density is really huge for these two systems and compared to batteries, whereas the energy density is higher for batteries and compared to batteries are supercapacitors. And then weight, if you see the conventional capacitors are in grams, so supercapacitors are really in 1 or 2 grams. Okay, whereas the batteries are in kilograms. So supercapacitors are further classified into 3 categories: EDLC capacitors, or redox capacitors, or hybrid capacitors. I don't want to go into the details. I just want to make you clear what is the exact difference between these capacitors or supercapacitors and batteries. Okay, those who are not clear still would able to visualize this slide. So here the similarity is both are running race. Okay, so but the difference is this is a 100-meter race, this is a marathon race. Okay, so the supercapacitors is nothing but it's a kind of capacitors. The capacitors can run only very short distance. but we can go for high speed. Here the speed is so important. The distance may be 100 meters or 200 meters, but the speed is so important. Whereas the distance is very higher, maybe 30 kilometers or 40 kilometers. Okay, here it is in meters. Here it is in kilometers. But here the speed is so not so important. Important, but it's not so important. Exactly the similar thing in the case of capacitors. Capacitors can run, you can charge or discharge. The energy stored in your capacitors can be taken back very quickly, or you can charge the capacitors very quickly. But the amount of energy stored in supercapacitors are small. So you cannot run a vehicle with supercapacitors. In such a case, you can charge your device every kilometers or every 2 kilometers, or worst case every 5 kilometers. Whereas in the case of batteries, you need not to charge your batteries for 400 kilometers or 500 kilometers. But the speed you cannot go more than 10 kilometers or 20 kilometers per hour. Okay, so that is a difference. Or the other side, you can visualize this. Supercapacitors are as like cup. Okay, so the amount of energy, that means the amount of water stored in the cup is small, but you can charge or discharge. If you want to empty, then you can simply pour it off, and then if you want to fill it, and then again you can simply you can fill it. So that's exactly the same thing. Okay, so if you see, the amount of water is small, charging and discharging is quick. Whereas in the case of water in the can, you could have some really in few liters, 20 liters or 50 liters. But here there is a restriction. You cannot empty the can quickly. You can slowly only you can empty. At the same time, if you want to fill it, that means if you charge your batteries, you have to charge very slowly, since this is a deciding factor. In fact, also the same way you can take only limited amount of energy. So that's exactly the difference between the batteries and the supercapacitors. So each has its unique applications. As I told you, batteries has some unique applications for mobile and all. We need not to drain our batteries very quickly. Our usage are limited. So you can use lithium-ion battery. Even if you use continuously drain, or for example, even if you might be observed when you watch a movie or when you play a game in your mobile, you could see your mobile will easily get heat, because you are trying to take more energy from your battery, lithium-ion battery, that is from your mobile. So because of this, the heat is produced. So if you repeat the same thing for several cycles, then obviously the performance of the battery will go. Then maybe the battery will fail after 3 months or 2 months. Okay. Whereas supercapacitor has its unique application like regenerative braking system. So for example, regenerative braking system is nothing but when you apply a brake, that mechanical energy, waste mechanical energy may be converted into electrical energy by using appropriate device. But if you have a battery, your battery may not able to accept all the electricity produced in a fraction of a second. Okay, it can absorb only slowly. So instead of that, you can have supercapacitors. So these are in market, people are using it. So here is one of the best example. I hope might be seen also in yesterday presentation by Dr. Kalpana ma'am. So here there is a bus. This is run with completely supercapacitors. As I told you, this bus can travel maximum of 7 miles. After 7 miles, again you have to charge. But wherever if you have this kind of charging systems, you can charge this bus. So only thing is this bus stop has this this kind of equipped with this kind of charging facility. But fortunately, the time required for charging maybe only 30 seconds or a minute. Okay, if you go for 30 seconds, you can make it a 50% of charging. So the bus is ready for going for another 7 or 8 kilometers. So the passengers come out and then new passengers goes in the bus stop. That time is sufficient for charging your supercapacitor. So again, this bus is ready to go for 7 kilometers. By the time you should get a next bus stop. So wherever there is a bus stop in 3 or 4 kilometers, particularly in cities, This kind of buses are very useful. This kind of buses cannot be used in highway or for long distance applications. Wherever cities like mega cities like Coimbatore or Chennai or Trichy, where you have the city buses run within the city, you could have the facility bus stop every 2 or 3 kilometers. Then this could be used. In the case of supercapacitors, there are a variety of options. Carbon-based materials can be used, or metal oxides, or phosphates, or sulfates can be used, or some polymers can be used as electrode materials. So I just put only a few examples of carbon materials and then what we have doing it at CSA AICTE, and then I'll close my presentations. So here the energy density of the, as I told you, the supercapacitors suffer from poor energy density. The power density of the supercapacitors are very high. So people are working on supercapacitors to increase the energy density of the supercapacitor. Okay. So the energy density depends upon this equation 1/2 CV square. So C is correspond to the capacitance. The capacitance is depends on these factors. The capacitance is depends on what is the surface area of your material and what is the structure of the carbon. Here not only a carbon, here any material. What is the structure of your electrode material? And that means morphology. Is a tube or sheet, or it is a porous or non-porous. So flower-like structure. There are different kind of morphology. And then what is the conductivity of that particular material? And what is the pore size or pore volume, or how much thick the pore, all these things. And what kind of functional groups are there in this material. So by tuning either one of these parameters or 2 or 3 or all the parameters, you can tune the capacitance. So that's why people can make n number of publications. Even you could see there are a lot of publication comes from the supercapacitors by varying the either one of the parameters, TiO2 nanorod, or TiO2 tube, or TiO2 spheres. Obviously the structure is different, the capacitance will be different. Also the conductivity may be different, or you can make a different kind of TiO2, so conductive by doping or by introducing some other material. You can tune the conductivity for a fixed structure. Then still you can also able to change the capacitance. So this is one of the interesting factor. The other one is the V. The voltage is mainly depends on the stability of the electrode material as well as the electrolyte which we are using it. For most of the case, people use carbon. Carbon is fortunately stable for very long potential window. So in such a case, the voltage is mainly depends on what kind of electrolyte. If you use aqueous-based electrolyte, I think yesterday we have seen the water will split into hydrogen and oxygen at 1.23 volt on volt. Or if you have over voltage, at the worst case is 1.6 or 1.7, it can split into hydrogen and oxygen. So if you use aqueous-based electrolyte, you cannot go beyond 1.23 theoretically. Some cases you can go up to 1.4 or 1.5. Worst case you can go up to 1.6 if you use aqueous-based electrolytes. Okay, but if you want to go for really high voltage like 3 volt or 5 volt, then you should use non-aqueous electrolyte or ionic liquid-based electrolytes. So coming back to the materials, particularly carbon-based materials, activated carbon can be used, or carbon nanotubes or carbon nanorods can be used. So this is always decorated with some pseudo-capacity material. I hope you are familiar with EDLC and then pseudo-capacitance. Here this EDLC comes from the carbon-based materials and pseudo-capacitance comes from this metal oxides or polymers. In that case, if we coming to the graphene again, it has a theoretical surface area of 2630 meters squared per gram. It's a highly promising material for electrochemical double layer capacitors due to the high surface area, and graphene is known for high conductivity. Okay, but unfortunately these graphene sheets are not stable. It will undergo restacking. So to avoid the restacking, people will use some metal oxide, some conductive polymers to act as a spacer molecules. So the EDLC comes from the sheets. The pseudo-capacitance comes from this metal oxide or polymer sheets. So here one of the interesting studies which we have done, maybe I will just quickly go through it and maybe another 5 minutes. You could see this graphene oxide. I simply put polyaniline. So what this case is happening is, this is you can see this is a TM image of sheet. It's a very transparent sheet, graphene oxide sheet. When I put polymer, there is a thick polymerization over the sheet. So the point of having this EDLC from this sheet and then pseudo capacitance from this polymer has been destroyed. Okay, because you have a very thick polyaniline coating. So this inside graphene may not be contributed to your DDLC capacitance. To avoid this, what we have done is we made a carbon nanofibers or some small carbon nanofibers like this. So we added some carbon nanotubes. So the carbon nanotubes will mix up. So when you add aniline, so the aniline get polymerized. So we thought that there will be a space to reach the graphene surface. But unfortunately, again this case, we end up with some very thick polymerization because this polymerization process is not controllable process. Okay. So you can control by varying the aniline, but still if you see, you cannot control the thickness of polymerization. But the other side, what we have done is, we have made a graphene sheet. We also made a manganese oxide nanosheets. We made a graphene manganese oxide stacking because the functional groups on this graphene surface has attraction with these manganese ions. So because of this, there is an interaction between the graphene and the manganese oxide sheet. So when you have graphene oxide dispersion, if you add manganese oxide nanosheets, you could have this kind of assembly because of electrostatic interaction. So then when you add some aniline solution without any polymerizing agent. So in the previous case, we used this polymerizing agent. Here, we will not add any polymerizing agent. So there is an oxidative polymerization process. That means the manganese 4 plus in this manganese oxide will become, it will reduce to manganese 2 plus and come into the solution. And then this electron go to this aniline and then it will get oxidized to get polymerized. It will initiate the polymerization. This process is called oxidative polymerization. In such a case, only this aniline, this manganese oxide has to come out, then only this aniline get polymerized inside. So in such a case, you can control the polymerization like this inside, in between the two sheets. You can end up with this kind of controlled polymerization of aniline. So you could have graphene polyaniline. So you could see this is the graphene polyaniline mixture we have got it. You could see highly porous in nature. In the previous case, you could see this is a very thick polymers has been formed. There is no porosity. Whereas you could see here, it's a highly porous in nature. We also confirm this using the TGA applications. Or we are using TGA. We have seen this is a graphene manganese oxide. So it has some 60% of manganese oxide. Whereas when you use aniline, this manganese oxide is removed and the aniline polyaniline get polymerized. So if you do that material, you could see that's almost zero. That means there is no manganese oxide residue in this material in this case. So the manganese oxide continue, everything is went on to the solution. We do have measured the surface area. This case is a 15 meters squared per gram, whereas manganese oxide route, if we make a graphene polyaniline composite, that is 58 meters squared per gram. So we have done some charge discharge characteristics. You could see this is a graphene polyaniline. It's a 468. This is, if we have carbon nanotubes, it's a 391. Whereas if you use this is a graphene oxide polyaniline.